So now we have a system that sends invalidation requests to shoot down copies. And we need to think about consistency model and the serialization requirement in shooting down these transactions, in shooting down these cache lines. So for instance, if I have two writes to the same location, okay, and they need to be serialized. We have to understand which one comes first, which one comes second. And we see that we have these, every transaction can take a long time now, request, reply, intervention. It takes a long time. How do we guarantee that two such transactions are properly serialized? And that's usually done using busy states. This is, by the way, two transactions to, let's say, the same cache line. If they're two different cache lines, they don't necessarily have to be serialized. Okay, so for instance, two write requests arrive at home. How do we know? How do we handle this? Okay, and this is usually done with busy state. For instance, you send a request to the home node. Home says, this is about address X. We're in some sort of transient state, so this is busy. And I'm sending an intervention to R. And let's say another request, let's call this L prime, now comes in with the request to the same line. Now that we see this is busy, we say, sorry, we can't handle both at the same time. Okay, so this obviously helps you to serialize it. You will wait for the whole chain to finish before you allow the second request to even come in. Okay, so that's the way you serialize. Now, if you have some transaction in busy state, how do you handle the new incoming request to the same line? There are a couple of options. Either one of them would work. You could buffer them at the home to say, well, let's wait, but let me put you in a buffer. But then the consequence is that you increase the chance of the buffer getting full. So usually that's not the preferred approach. Okay. Knacking and retry is the typical approach. Oh, sorry, we're busy, come back later. And we see sometimes this is also handled by forward the request to the new dirty node. Well, I know this is busy, but this node L is going to be the new owner. Why don't you talk to him? So we'll see how this is actually done in reality. So this serialization here really means if you have transactions to the same location, how do we order them? Okay. A related issue is when I start to write to a memory location, when does it finish? When is it completed? Okay, so it's completed when the old copy is gone. So suppose if I have a requester, home node, and a couple of sharers shown in this animation over here. The first step would be the requester telling the home I want to write. The home would, let's say in a particular style of messaging, tell everybody to shoot down their line. And it will also, this is probably not very visible, this is tool, perhaps really simultaneously, sending a reply to the requester to say, expect two sharers to send you acknowledgement. And finally, when this acknowledgement arrives, that's when we know, all the models, all the sharers have invalidated their copy, the previous write transaction has completed. Okay, so when do we need this? In a relaxed consistency model, write completion is usually not something that we care about unless we see a fence. Okay, that we need to order things. Remember, in the most common thing, in the most common cases, transactions are not necessarily ordered in a relaxed consistency model. If you have sequential consistency, or you just want to support write atomicity, you also need to know when the write completes. For instance, in write atomicity, you know when the write is completed globally. That's when you allow the read to get a new value. Remember this example that we have. If write is not atomic, then this program will print out A possibly equals 0, and that's potentially confusing. When we have write atomicity, it will not print out 0. When we were in the bus space system, write completion, write atomicity is inherent, because the minute we get the bus, that's our transaction, and we're invalidating everybody in one go, and we guarantee by the end of that write transaction, we're done. In this directory-based protocol, we don't have that inherent atomicity. Okay, so what we're doing is again using the same technique. We have busy state. Okay, so the directory remembers that we're currently busy finishing the previous write. Therefore, during this time period, if there is a read request to the cache line, we will nag, we will reject the request to be retried later. Okay. Now, a lot of this is really that it has to appear in that case, that write has to appear atomic. Doesn't necessarily mean you have to do any of the thing that we were discussing, that you absolutely have to do that. As long as you can reason that it will have the same appearance, it will work. I will give you an example. You can actually allow early read. Remember, we were talking about how you prevent violation of write atomicity. A typical way is to deny early read. Before I erased all the old copy, I'm not going to allow the new copy to be seen by anybody. Is that necessarily it's a sufficient condition? It's not a necessary condition. You don't necessarily have to do what is typically done. I'll give you an example. The purpose of the example is not to show you that you should do this, and in fact, that's why there's a reason why people typically implement the simpler approach. But this is just to explain that it will work. Okay, so if we allow write to be read early, if we allow early read, does that necessarily violate write atomicity? No. We have to propagate the tracking of write completion. Let me show you the example. So remember this code that we have, right? When we want this to work properly in a relaxed consistency model, we need a fence over here. Because without the fence, we're saying these transactions aren't necessarily ordered. Then we would be in trouble. We can execute b equal to 1, potentially allow b equal 1 to happen. Okay? And because of that, there should be a fence. So now if the invalidation is still pending and we allow an early read, remember there is the invalidation to this copy. While this is pending, the typical solution is not to allow P2 to go back and read the value. But suppose for a moment we do allow, but the read is to a memory location that we haven't finished the write yet. Globally, we haven't. So the read can be allowed to take place, but it cannot be allowed to finish. Therefore, you cannot go through the fence. Okay, so this is interesting. You are allowed to read a equal to 1. You can execute the instruction, but it cannot be considered to be completed. Therefore, you cannot go through the fence. Similarly, let's say I have sequential consistency, okay? And let's just say I'm allowing early read. The read can happen. ALU instructions, depending on the read, can continue to use the value. but the load cannot be retired because the write is not globally performed. And when you read from that globally not yet performed write, you're not allowed to perform. Because remember, because you're sourcing from that value, you're supposed to come in the program or in the order, in the global ordering after that write, and that write hasn't finished, you cannot be allowed to finish. Okay, so again, like I said, this is not to advocate you should do things like that. It's probably too complicated to propagate this tracking of write completion, this responsibility. But you can do that. So the whole point is, when you're not allowed to do something, that doesn't mean you cannot do it speculatively. All you have to do is to make sure that you're not allowed to finish the operation so that it appears in the global order that it has already been done. So we all know that cache coherence protocols are very complex when you're designing them, especially the ones that are in the real world, because there are lots of performance enhancement. After all, that's why we pursue multiprocessors, to have high performance, high reliability. So the performance improvement adds complexity, makes correctness more difficult to ensure. And it has a lot of subtle corner cases, meaning things that corner case being it's not a common case. You have to think about them. So it's not a dire situation, because the more you deal with this, the more experience you have. So this understanding will help make the job easier. On the other hand, there are automatic verification techniques that are being used. They're important. I'm not very familiar with these tools in real life personally, but they are being used by the processor vendors. So we will look at an example just to get an idea of how in real world application it's going to get messier than what we are covering in the class. We're covering kind of examples. These are by no means everything. So not sure what's happening here. So we're going to look at a very old machine. Back in the days when I was in grad school, we got one of the university got one of these machines, Origin 2000, and all of a sudden I can launch a lot of jobs, simulation jobs. I was very happy, and it's a very modern machine back at the time, but it was also done based on really an academic prototype, so it was quite exhilarating experience for a researcher in the area. What you just read in the paper 10 years ago was actually being adopted in a real-world product. So the idea is you take commercial off-the-shelf component as much as possible. You don't redesign the microprocessor, for instance. You don't redesign the I/O system, the peripherals. You take as much as possible, and you build perhaps a chassis and specialized connection to make it a multiprocessor. And that's what it is here. We can zoom in and look at this just a little bit. It's an R10K based system. It has two processors that you can see. What you're really seeing, of course, is the heatsink itself. And then you have lots of memory. And this is really something that you probably wouldn't appreciate until you open up one of these big machines. It's all main memory. Okay. It wouldn't be very different in today's machine. I think later on I do have. Oh, I'm sorry. It's something that I already showed early on. How most of the components seem to be memory components. So the real thing that you're designing in this machine is the controller. They call it the hub. It's a piece of ASIC that they designed specifically for this system. And we will see that there is some potential extension, and this has to do with the directory. And the rest of it is really just, you will see, we'll see in the logical diagram, there's some buffer, okay, what's called bus control, some peripheral like that, a lot of power delivery support, and of course the connection to integrate with other nodes. So the board, the node, is basically consisting of two processors with a whole bunch of memory, as shown in here. We already saw that. It's really how it's done. The hub is the one that is in control of the coherence protocol. And this is a fairly sophisticated piece of custom logic. Of course, this was very old, so it was just about sub-micron. Each processor has outstanding transaction buffers, and they have some block transfer engine, okay, to do fast copying. And the interface is connected to network power and so forth, and this is to connect to the backplane. So when you have maybe this view, really what happens is you have these blades. Well, they're not actually blades, but racks, and they're connected in the backplane to communicate. So you support a lot of these machines. The router has a pretty big, at the moment, it has a fairly good bandwidth, gigabyte per second. These machines are operating at 200 megahertz, very old, but again, the whole principle works just the same today, and it was pretty scalable at the time. You can have 500 nodes, bringing this to a kilo processor. Of course, nothing close to gigantic machines where they're typically message passing based. Within a node, so the coherence is actually in the unit of node. Okay, so when we decide which machine, which processor has a particular cache line, it was recorded as in node. And within each node, it's really just two processors that the hub would individually poke to know each processor. It's not actually done in a Snoopy coherence protocol. And the directory format can change depending on the size of the machine. So you can have up to 512 machines, but in these markets, what you usually do is you sell a lot more low-end systems, 32 processor versions, than you sell the 1000 processor version. So you don't want to overtax the system. You don't want to have a machine that has the in-field scalability to 1000 and bring all the basic costs with you. So there's some slots. You'll populate those slots when you really need it. We'll see just in a while how this is done. And when you have 512 nodes together, you need to think about interconnect. And the interconnect, we're going to cover the whole theory of interconnect in a much later time. But roughly, this is the way that this can be done in this machine. It's really some sort of a mesh or cube that you can expand. When you have a very small number, 8 processor, for instance, then there are only 4 nodes. Okay. And what they will do is they have routers connecting to 2 nodes and 2 routers connected together. So each one of these is a node. Okay, so by the same token, if you build one of these routers, you can connect to, in their case, it's a 6-dimension router, 6-port router. Which is shown here, right? So you have a 6-port router that allows you to connect to 6 nodes. In the low-end system, each router is connected to more than 1 node because you have abundance of port. So in this case, each router is You can even have a router connected to all 4 nodes, but what they chose to do is to have 2 routers, each connecting to 2 nodes, so you can keep on doing this, okay, and expanding. So now each router is connected to 4 nodes or to 4 ports, 2 directly to nodes, the other 2 to other routers. And you can scale this up to the point of a hypercube. So this is a 3-dimensional network, and this becomes a 4-dimensional network. So you have 4 neighbors. That's what occupies the 4 nodes, the 4 ports, and then you have 2 other nodes connected to real nodes, to one of these guys. This is a node. So that gives you, as you can see, 32 nodes times times 2 processors per node. This is a lot of numbers, right? Remember, 2 processors per node. So you can have up to 64 processors. So this is probably considered to be the smaller scale size of the system. 64 processors, that's usually quite enough. And when you want the biggest machine, then you actually have to have routers that's just dedicated to connecting different chassis, if you wish. So what's shown here is an example of how do you scale to 64 node. You can no longer do what's shown in here. Okay, that has a maximum of 32 nodes. So when you want to have more, what they do is they have system like that. They bring in a meta router. They call this a meta router. They connect. The meta routers are only used to connect to these individual islands. So you can have one there, another to connect a different position of the router in each cube. So we will see that this is really not a trivial thing. Every time you have a router access to go through one of these routers, at that point it was 41 nanosecond. Now, remember, this is a 200 megahertz clock frequency processor. So 41 nanosecond is not as long as we think of today. It was a couple of cycles, 8 to be a bit more precise, right? So these are 8 cycles. So nonetheless, and if you want to move from one node to another node in another system, you may have to go through a lot of these hops, and there is corresponding queuing delay to be reckoned with. We'll see all of that when we talk about interconnect. Here, all I want you to understand is usually there are really 2 things. That it's a general purpose interconnect that you can change the topology based on how many nodes you want, right? And that has implication. So it is scalable, perhaps in total bandwidth, but latency gets worse. So it's not scalable in the ideal sense that regardless of the scale of the machine, the node performs just as well in all cases. And that is the interconnect, and this is what you have to send and receive message with in your coherence protocol. So now we assume this is a black box. Okay, we have the interconnect. We need to send a message. We will. It won't necessarily arrive in order. Okay, so if we need any guarantee of delivery, we need to have acknowledgement. So if I send you an invalidation, I cannot say let's wait for X cycles and we guarantee you will get it. No, we have to have explicit acknowledgement. Now that we know this is the the fabric with which we send messages, now let's think about the coherence protocol. And it uses a directory because there could be up to 24 processors or 512 nodes. You need to remember who has what. So broadcast is not a solution. So there are 3 directory formats. Okay. If the cache line is an exclusive state, dirty, whatever, okay, only one processor has it, then we can record exactly which processor has it, not just the node. Okay, within each node there are 2 processors. So in the biggest system, this costs you 10 bits, and you can have that, right? Because really the smallest directory that you have is in this system is going to be 16-bit. So 10-bit is more than enough to remember to point to which exact processor has the exclusive data. When it is in shared mode, now you need to remember potentially up to 512 processors or nodes. So how do you do that? And they use vector, bit vector. So if I have 16 bits, right, it would just be a bit vector, 16 of those, each representing a node, and this can give you up to 32 processors. Remember again, a node contains 2 processors, and the coherence protocol didn't really treat them independently. So if I want to invalidate, I send to the node hub. Okay? The hub of the node would then individually investigate each processor's state to decide on the proper treatment. What if you have a big machine, the biggest machine? Oh, too bad. You need more storage. So what they built was actually fairly interesting. If we just go back a little bit, the memory was not exactly commodity. And if you look at this, the chips are commodity. Okay, so you buy these chips, memory chips, but the DIMM is proprietary. It's something that they have. So that gives you the main memory and 16 bits of hierarchy, of directory. So I don't actually remember the size of the cache line, but let's say 64 byte or thereabout, or 32 or 128. So every 64 byte of cache of a line, a unit, would be equipped with 16 bit. Okay, so that's about 2 byte per 64 bytes. So it's about 3% extra overhead. So that's considered acceptable. And this is what you have in every machine, no matter what the size is. If you want to buy a big machine, you will have some extra space to put in, to plug in new memory, which is of a different type, different form factor, okay, much smaller. As you can see, you buy those, and that supports 64-bit. So now the coherence, now the directory overhead is something about maybe 10%. Again, this depends on the cache line size, which I don't recall at the moment. And when you have 64-bit, okay, that can easily allow you to address 128 processors. But that's not enough, remember? We can have up to 1024 processors. Okay, so that's, if you buy a machine up to 32 processor, you don't need to buy more storage. If you buy between 32 and 128, you have to buy more storage. And beyond that, you do buy the same storage of 64, and now the coherence protocol becomes coarser. So since we have 64 bits, we can represent 64 groups. And if you have 1024 processor or 512 nodes, then each bit represents 8 nodes now. So anytime you want to investigate, you say, let's invalidate, you have to send a message to all 8 nodes, just in case, not just in case, to make sure that you can cover what the bit is representing. Okay. So invalidation will be sent to all hubs in the group, and that's coarse vector. And the machine can choose between these two dynamically. Okay, it's not a hardwired thing, and that can be configured in the field. Okay, so for the discussion below that, after this, we will not worry about the course vector. We just say there's a directory, and then anybody who has a copy of a particular data will receive corresponding directory messages. So the format side is done. So let's go on to the state side. So the messy state that we're comfortable with is actually the cache side, not the directory side. What do I mean by that? So if you have a processor owning a particular cache in modified state, for that processor, you can actually read, right? Your data is up to date. But the directory would have to remember, oh, this is in modified state in someone else, in cache. Don't read from the home. The memory content is not up to date. Okay, so the directory has its own states. In particular, there's a state called unknown, which means nobody has a copy. Okay, the memory copy is the only copy available. That line is not in any cache. And if the data is in shared state in any set of nodes, then the directory state is in shared. If the processor, if the machine, if the cache line is in modified state or exclusive state, the directory says it's an exclusive state and point to the owner. So we don't know whether it's modified or not, but we know which node is in either one of the state. Besides these three states, so basically the directory didn't make a difference between M and E. Besides these three, there are three busy states or pending states. Remember, now the transaction is necessarily non-atomic. It involves one node initiating a request to the directory and directory acting on its behalf, and so on and so forth until the dust settles, so to speak. So we have all these busy states. What are these busy states? The current state is in E, but someone wants to read. Fine. The current state is in E, but someone wants to write, and that's called a read exclusive, right? We want to get the line. We don't have it, but we want exclusive ownership to it so that we can potentially write to it. And there is some special cases. Sometimes you support pages that are not allowed to be cached, and any read would be an uncached read. Finally, I'll tell the story a bit later, but there is a state to allow page migration, and this will become more interesting when we discuss NUMA versus COMA. So about page migration, the general idea is where you put a piece of page or the physical page in the system matters. If you put it in the wrong place, then when there is a cache miss, you have to initiate a remote access, maybe from a faraway node, and that's bad. So maybe we should remap the page at a different location. We'll worry about this later. But when we want to do page migration, we have to worry about all the cache lines throughout the state, and this is when we give it a special state called poison state. So we can ignore that for now. Let's think about the non-special case of page migration. Let's ignore the page migration for now, and we will see. So now we know that we have this state. We also know the cache side controller has four stable states, and we want to think about how you handle read and write request. It's fairly straightforward in principle. Okay, if I want to read, if a cache wants to read and I don't have it, what do? I send it to the directory. The directory will say, fine, let's look at the state. If it's already in shared state, what happens? I'll give you the data, and I'll just remember you are another sharer, and so on and so forth, right? So this is the general idea. It's not very different from snooping-based coherence, except snoop is very convenient. When we have a shared medium, we can say invalidate everybody. Okay, we can assert, do you have a copy? If so, please self-invalidate. Now we can't do that. We have to send individual messages. What I do want you to do is the following. And we usually do this on a piece of paper. This is the state that the directory can be in: unknown, shared, exclusive. And the processor can issue these different requests. Okay, a simple read. I don't want to do anything. I want shared mode. I want shared write. Upgrade is the case where I have the data already, but it's in shared state, and I want exclusive state. So this is similar to read exclusive, where I want the exclusive state. Hence, it's called read exclusive. But in read exclusive, I also don't have the data. So I need you to give me both the cache line data and to make sure that everybody else invalidates their copy, so I have the exclusive copy. So this is with data. This is without data. I don't need you to give me data. I already have it. That's the only difference. Finally, if I have a cache line, it's already dirty. I just keep on having it in dirty, but one day it may be evicted to make space for another cache line, and that's when we write back. So that's what the processor can issue for different types of transaction. And the state, and we're ignoring the poison state. So there are 3 busy states. As you can see, this is going to be oversimplified. We don't really care about a lot of the details. Okay, and think about what will happen. And what if the cache line is in this state? What happens? Okay, what happens? What, I'll give you a hint. So for instance, if it's an unknown state, someone wants to issue a read, okay, what do you think happens? After this, what would be the state? Okay, and then we can say, well, okay, we're going to supply the data. Supply data, right? And what's the next state? So from unknown to, is it shared state or is it E state? It's E state, right? Exclusive, because you're the only one having it. And then we have to remember who did it, right? So the requester, we have to record the pointer to the node. That's about it, right? If you think about it, that's the sensible thing to do. So what I'm asking you to do now is, well, the video is going to end soon. Take that piece of paper, take about 30 minutes to fill it out. It's roughly how much time it takes if you think you know what to do. Okay, most of this should be straightforward, but there are a couple of corner cases. That's the key point that we want to emphasize, that you need to worry about. It's not, you cannot just design for what you think is going to happen, or what is the intuitive outcome. The outcome is actually more slightly stranger than that, because this and this might happen. So you really have to go through this exercise. Please fill it.